Okay, we've got a vectors question. We're given the point A, the point B, and a line. The first thing we've got to do is get the distance between A and B. And to get started on that, you work out the vector AB, so you know what to do with OA and OB, which are these numbers in column vector form, to get AB, and then you Pythagoras it, and you give your answer in a nice exact form. Then we've got to find an acute angle between the lines AB and L. Well, we've got the vector AB, we need to get a vector for the line L. And what matters when you're finding angles, of course, is just the directions of things. So from this entire recipe for the line, you've just got to pick out the direction vector. So you've got the vector AB from before, we've now got a direction vector from the line, somehow. And once you've got two column vectors, you need to work out the angle between them. Your recipe for that is in your notes. It's to do with the dot product of two vectors, the scalar product. Look up the method in your notes for getting the angle between two vectors. In this case, you may, if your vectors happen to be oriented in a particular way, get an obtuse angle first. That's okay for the angle between two vectors, but this is insisting on an acute angle, because we've actually got lines. So the vectors you've got will be in the right directions, but if you imagine extending them to form lines, there'll always be an acute angle, and you can get that by subtracting an obtuse angle, if you've got one, from 180 degrees, and that will give you the angle you need. Then finally, point C. This is one of the kinds of things where you probably want to draw a picture to help you visualize what's going on, because sometimes there's an easy parallelogram or something that helps you get the answer quickly. In this particular case, there isn't an obvious quick method to get there, so you actually have to work with the distance AC and the distance AB. Now the distance AB we've already got, so that's okay. The distance AC, we need to start with the vector from A to C, and we've got the vector from O to A, so we need the position vector of C, we need OC. But all we know about C is that C is on the line. So this thing here is our template for the vector OC. For a particular value of lambda, we can generate any point we like on the line, including C. So OC is just this thing here. You can leave the parameter as lambda, or you can call it little c, or whatever you like best. But it's going to be, for the x bit, it's going to be 5 plus the parameter times 1. I'll just leave it as lambda. And you do similar things for y and z. So you've got a vector for OC, which has got lambdas in it. And then for AC, you're going to do a subtraction of two vectors, one of which is this one, and the other of which will be the position vector of A. And again, you'll end up with a vector which will have lambda sprinkled around in it. And then you've got to find, you've got to make the magnitude of this vector equal to the magnitude of AB that you found before. So you've Pythagoras this, and this has got lambda sprinkled around in it. So you're going to have brackets with lambdas in being squared, equaling what you found here for the distance AB. Well, technically you'll have the square root of all of this, and you had a square root before, but you can get rid of the square root straight away. Square out the brackets, and you're going to get a quadratic equation in lambda. So you solve the quadratic, get two values for lambda. One of them will give you the point C, and the other one will give you a different point, and you should be able to decide, if you think clearly, about which of those 2 points you want. As a hint, the other one has already got a letter, and is not the one you're finding.